Welcome back to gases. In part 3 of this unit, we're going to be looking at the gas laws, Dalton's law, and Graham's law. Let's get started. Okay, so first with Dalton's law, what he says is for a mixture of gases in a container, the total pressure exerted is the sum of the pressures that each gas would exert if it were alone. So this is the total pressure is equal to pressure 1 plus pressure 2 plus pressure 3 plus so on and so on and so forth. The pressure results then from the relative amount of a gas, not its identity. So it doesn't matter whether the gas is carbon dioxide or oxygen or nitrogen or helium. Add the individual pressures together and that'll give you the total. Also, his law says that pressure is proportional to moles. So if you increase the amount of gas while keeping volume and temperature constant, then you'll increase the pressure that that gas is putting on the walls of its container. Let's look at an example problem. 0.25 moles of CO2, 0.25 moles, and 1.5 moles of oxygen have a volume of 20 liters at a total pressure of 3.5 atmospheres. Now that's a total pressure, not a total moles, so I'm going to write it over here on this side. Find the mole fraction or partial pressure of each gas and the volume of each gas. So first of all, I've got a total. I'm going to find the total number of moles. This is 0.25 plus 1.5 is 1.75 moles total. And let's remember what mole fraction is all about. Mole fraction is the part moles divided by the whole moles. So if I was looking for the mole fraction of CO2, that'd be 0.25 over 1.75. Remember mole fraction, you don't have to multiply by 100, so it's just that. And you get 0.143. Essentially, that's trying to tell us that 14.3% of the moles of the gas are carbon dioxide. And so, because 14.3% of the moles of the gas are carbon dioxide, 14.3% of the atmospheres, the 3.5 total, is carbon dioxide. So if I wanted to figure out what the pressure was of the carbon dioxide individually, that would be something like this. Oxygen is 0.25 out of a total 1.75 moles, so what is the pressure out of a total 3.5 atmospheres? So this is a cross multiply and divide kind of situation, and X is going to be equal to 0.5 atmospheres. Now for oxygen, we can really just use the other numbers that we have. So let me see, let me grab a different color. Since the total is 3.5 and the carbon dioxide is 0.5, the oxygen's got to be 3.0. And since mole fractions add up to 1 minus 0.143 is 0.847 for the mole fraction of oxygen. Or you could actually solve it out, which is probably not a bad idea just to check yourself. 1.5 out of 1.75 is equal to 0.847. And 1.5 out of 1.75, x over 3.5, x is equal to 3.0. It's a good idea to check your math to make sure you didn't mess up somewhere. Okay, so then the very last part that the question is asking, again, let me change colors. What is the volume of each gas? Well, it's in a 20-liter container. Since it's in a 20-liter container and gases fill up their container, the oxygen takes up a volume of 20 liters. And the carbon dioxide takes up a volume of 20 liters. Both of the gases have the exact same volume. Volumes are not additive for gases. Pressures are, moles are, but volumes are not additive. Let's look at another problem. Suppose you collected oxygen over water at 20 degrees and a total pressure of 738 torr. The volume of the gas is 310 milliliters. So 20 degrees C, 738 torr. The volume is 310 milliliters. Calculate the volume of the dry oxygen at 20 degrees C, so a constant temperature, and 765 torr. That's all the information from my problem. let's talk about what it means to collect oxygen over water. So you have some experiment that's releasing some gas in this container. And as the gas is being released, it's going up this tube and going down this tube and going up into this tube and being collected. Gas 1 is being collected at the top of this container, which is, I guess, why it says here gas 1. But the problem is, when that gas is bubbling up through the water, it's also collecting water. It's like pulling water with it. So there's water vapor as well at the top of that tube. So if I want to figure out the pressure of the water vapor on its own, or sorry, the gas 1 on its own, I'll have to subtract out the pressure of the water vapor. So 738 torr is the pressure of both gas 1 and the water vapor. So if the water vapor itself is 18, 738 minus 18 is equal to 720. Means the oxygen gas has a pressure of 720 torr, the dry oxygen gas. And it's asking about the dry oxygen at 765, so I don't have to subtract that from 765. Now I've got a gas law problem. Notice my temperature is constant, my pressure increases. What should happen to volume? If pressure goes up, volume should go down. We have P1V1 equals P2V2. Let's plug them in. Make sure you're using 720 torr, not 738 torr. So we've got 720 times 310 divided by 765. Hopefully you're going to get 292 milliliters. And that's my final answer. Let's look at the next problem. If 40 liters of nitrogen gas are collected over water at 22 degrees, so this is the wet gas, when the atmospheric pressure is 750 torr, what is the volume of the dry gas at STP? So remember, STP, standard temperature and pressure, is 0 degrees Celsius, not 25 degrees Celsius. And STP is 1 atmosphere, or 760 torr. Here I'm going to use 760 torr because they already gave me a torr, just to make sure the units will match up. Also, don't forget, every single time you see Celsius, change it into Kelvin. Always, no matter what, always, 22 plus 273 is 295. Okay, make sure you're always using Kelvin temperature. So the Dalton's law part of this problem says that 750 torr of pressure is the wet pressure. So you'll have to subtract out the water vapor pressure at that temperature. So 750 minus 20 is equal to 730 torr. That is the new initial pressure instead of the 750 torr. The 760 we're going to leave alone because that's the dry nitrogen at STP. So this is a combined gas law problem. Pause the video now. Solve this one on your own. Okay, I hope that you actually did that. Let's see. Temperature's going down. Volume should be going down. Pressure is going up. Volume should be going down. So I'm going to expect an answer smaller than 40. P1V1 over T1. P2V2 over T2. So plugging that in, not 750 torr. Make sure you're using 730 torr. So these are all my initial conditions and my final conditions at STP. When you're solving this in your calculator, you're multiplying the numbers that are across from each other that don't include the x, and then dividing by everything that's left. So you end up having 730 times 40 times 273 divided by 295 divided by 760. And hopefully your x is equal to 36.5 liters. That's your new volume. Okay, that was Dalton's law. Let's look at Graham's. Graham's law says that the rate of effusion of a gas is inversely proportional to the square root of the mass of its particles. So the rate of effusion, like the velocity, VEL, that's my velocity of, say, one gas, compared to VEL, that's my velocity of the second gas, is inversely proportional to the square root of their masses. So let's just say molar masses, because then that's both the mass of a mole. That's GMM2 over GMM1. The GMM is the molar mass, or they could be both of them the mass of a particular volume. But what's important here is to notice that the velocity of the second one on the bottom and the molar mass of the second one on the top, because we want it to be inversely related instead of directly related. The AP test is not interested in you knowing the actual calculation formula, but just that a smaller gas or a lighter gas will move faster than a heavier or larger gas. Let's look at a math problem to deal with this. Given helium and oxygen, which travels faster and how much faster? So first of all, helium travels faster because helium weighs less than oxygen. The molecules are smaller, the molecules can move faster. Which travels faster? Helium. But how much faster is your math problem? So if we're going to look at the velocity of helium compared to the velocity of oxygen, we want the inverse of the square root of their masses. So oxygen is going to be on top, 32 because it's O2, over 4 for helium. Make that a little bit prettier. 32 over 4 is 8, so that's the square root of 8. Please solve that out to get an actual decimal number of 2.83, which means helium travels faster. How much faster? 2.83 times faster. One more. A store receives a shipment of defective balloons. Each one has a tiny pinhole of the same size. If one balloon is filled with helium and the other is filled with air to the same volume and pressure, which balloon will deflate faster and by how much faster? So helium is a very small gas. Weighs less, it will deflate faster. The helium is going to escape from a small pinhole in a balloon faster than air will because helium has a smaller molecule. But by how much? So if I'm going to compare the velocity of helium to the velocity of air, I need the inverse of the square root of their masses. Now, notice this time they're both in 1 liter. So all I have to do is look at the grams. I can directly compare the grams. That's the grams of air on top and the grams of helium on the bottom. So the square root of 1.2 over 0.16, square root of 7.5, which is equal to 2.74. Sorry, I said 7.4. 2.74. So helium will escape faster. How much faster? 2.74 times faster. Which means if it takes 1 second for the helium to escape, it'll take 2.74 seconds for the air to escape. Or if it takes 1 hour for the helium to escape, it'll take 2.74 hours for the air to escape. This is why if you have a balloon, here's my pretty balloon, that you buy from the store, and it's floating, and then you have another balloon that you buy from the store, but you filled it up with your own air, it's going to kind of sink. But the balloon with helium in it will sink and deflate much faster than the balloon with air in it. The air balloon's going to stay on the ground the whole time, but the size will stay larger for much longer because the air molecules are larger than the helium molecules, so it takes longer for them to escape out of the balloon. Okay, that's Dalton's law and Graham's law. We'll see you next time for molar volume and ideal gas law.